I'm pleased to talk to you about health inequality and pain. And let me hit the page down. So what I want to talk about in general is what are the issues with regard to health inequalities. So it's ubiquitous. Whenever anyone measures health status by something or other, there's variation. But there's a big question about, is all of this variation good or bad? Is it morally just, or is it in some sense unjust? And in order to assess that, there's the idea of counterfactuals. What if a given source of health inequality were absent? But in order to answer such what if questions, we need to construct the counterfactuals, and in order to do a reasonable or plausible job, I'm not going to say a perfect job, we need to be able to characterize empirically the web of causality, the way different factors interact, and do so in adequate detail. When one looks at the literature, certainly my view is that I see more or less two disjoint strands in the literature. The philosophers like to talk about, in prose, when a particular source of inequality is just or unjust, and the empirical researchers like to measure how much inequality there is, but they generally avoid making any moral judgments beyond simply saying, or implicitly saying, that health inequalities are bad. The way I'm going to approach this is, I still think, somewhat novel, although I wish it weren't so novel. We're going to use a micro-simulation model, in particular a HealthPaths model. I forgot to say at the beginning that this model was funded when I became a research chair by the Canadian Foundation for Innovation, and I should recognize my colleagues Vid Bialik and Jeff Rowe, who've done spectacular work in putting all of this together. So we're going to use highly detailed statistical analysis of longitudinal data, but the statistical analysis itself wasn't done first and then the modeling second. The statistical analysis was designed from the start to feed into a micro-simulation model. As you see, the statistical analysis is complicated enough. There's no way that by simple inspection of coefficients you could tell what's going on. So then we're going to use the empirical results in order to simulate these counterfactuals. What if those sources of inequality that are easily agreed to be unjust were removed? And we're going to try out some data visualization and see if that works. So there are various definitions of health inequalities. I think one of the earliest was Julian Legrand looking at life tables and the survival curve and saying, if everybody died at exactly the same age, there would be no health inequality. Let's call that a univariate approach to health inequality. But then there's, I have a quote here from the World Bank, where health inequality is associated with some other factor, and most often socioeconomic status. They sort of treat inequality and inequity as the same word. But in essence, what we see there is a bivariate concept of inequality. If you think of a scatter plot of people on a vertical axis, you have some measure of health. On the horizontal axis, you have some measure of socioeconomic status. And if there's a correlation, then there's a bivariate relationship. There's also sometimes reference to groups, like by race, ethnicity, things like that, social groups, Braverman and company. So there it's still bivariate, but it's using a categorical rather than a continuous or more general kind of variable. Why is this salient? Well, one of the reasons, there's the phrase, beware the mean, right? The person who drowned crossing the river that was on average 20 centimeters deep. So there are well-intentioned population health interventions like smoking cessation campaigns and asthma management programs. But because the better educated segments of the population are more likely to take up and change their behavior based on that information, while overall it may raise the level of health, reduce the amount of asthma, or reduce the amount of smoking and associated lung cancer and heart disease, it also may increase the degree of inequality as the better off people improve their health to a greater degree. So there are a number of definitions that have been used to describe the unjust inequalities. And Asada, Hausman, for example, say health inequality is unjust or unfair or inequitable if it's due to factors related to unequal opportunities or it's amenable to policy interventions. On the other hand, Angus Deaton, a recent Nobel laureate, said, well, if it's plausibly attributed to freely undertaken personal choices, then that's fine. And I suspect that Angus was thinking about skydiving. So if you kill yourself jumping out of an airplane, too bad, so sad. But then I have to ask, what about Médecins Sans Frontières? There are people who are dedicating their lives and sometimes losing their lives. Those are freely chosen activities. Is it unfair that they die combating the Ebola epidemic? Angus Deaton also says, well, what really matters is if you're a bit yuckier in health, if you've got something else that compensates, you won the lottery, so you got a pile of money, we're not going to care about the inequality in health because we're going to put it in a broader framework. I don't want to disagree with that approach, but as a result, the ameliorable kinds of health inequalities I want to look at are ones that are unlikely to affect significantly your other, to the extent you believe in welfare functions, the other components of welfare. So as I've already said, it's important to distinguish univariate and bivariate approaches. I had the opportunity to sit in a room with Chris Murray and Michael Marmot at one point at WHO, and they both had red faces. They were arguing so vehemently about Chris preferred the univariate approach, and Marmot, Whitehall study and all that stuff. Absolutely got to have a bivariate approach. I think most prevalent is the bivariate approach. And Julian Legrand's stuff seems to be kind of a backwater, the univariate distribution. And I used to be totally on the side of, if we're going to talk about health inequalities, we should talk about bivariate inequalities. But if one of the factors that we want to look at is socioeconomic status differences, then wait a minute, I'm confused, I'm confounding or I'm embedding one of the causes with the way I measure it. So I think we need to have a metric or way of measuring health inequalities that's independent of socioeconomic status, and that's going to be the univariate. Now, a few bits on how we observe this sort of thing. There's a lot of people who publish papers by looking at cross-sectional surveys, or they look at mortality rates across small areas. These are essentially cross-sectional, and they treat health status while living separately from mortality. But in this analysis, I want to take a more comprehensive view. So I want to bring together health status and mortality, and I want to look at full life cycle, not particular age groups. And how do we do this? This is a conventional, the outer boundary survival curve is stylized, and you see different gray shade levels. You can ignore the disability-free life expectancy line there. That's another group of people. If you take the weighted area under the survival curve, where the weights are some measure of how healthy or yucky you feel, or you are, measured by some scalar health status measure, then you get something that's not life expectancy. There are various names, but I'll call it health-adjusted life expectancy, and that's the variable I want to include. Now, if we're in the world of Julian Legrand and univariate health inequality, there would be, if we want to talk about complete equality, there would be no difference in the ages at death. Everybody would die at exactly the same age. If we're talking about bivariate health inequality, here's some research from using HALE, health adjusted life expectancy, from my former colleagues at StatCan. So these are income deciles along the horizontal axis and various measures, health adjusted life expectancy in each decile, excuse me, on the vertical axis for males and females. And if there was complete equality in this kind of bivariate measure of health inequality, all of those bars would be exactly the same height. So how do we bridge the moral philosophy and the empirical analysis? We're going to posit a web of causality. Nancy Krieger has a nice paper about that. So we're going to not canvass everything, but we're going to go through the literature and say, what are some of the key factors here that have strong empirical support, albeit in a piecemeal fashion, and include them in the analysis. We're going to then use statistical analysis to quantify all of the pathways in this web of causality. And we need to recognize that everything affects it. It can affect everything else. There's no particular priors that my co-authors and I have imposed on this analysis. And we're going to embed the results in the tightly coupled HealthPaths model, as I said, and then we're going to use the what-if stuff. This is far more sophisticated than conventional things you may have heard of. Cause-deleted life expectancy. What if there was no cancer? People use life tables for that. It's really rinky-dink, if you'll pardon my language, because there's no way you're going to eliminate cancer without eliminating smoking. And if you eliminate smoking, you're also going to greatly reduce heart disease and stroke. So what are the main ideas and innovations in this HealthPaths model? We're going to focus on the determinants of health-adjusted life expectancy. So that's, just think of HALE, that weighted area under the survival curve. That's a complex object. You can't make it into a simple dependent variable in a regression. We're going to go beyond the simple population attributable fractions and categorical attribution, include heterogeneity, very important. And we're going to focus on functional health. I know most people, when they think of health, think of biomedical diseases and biomarkers like cholesterol. We're going to ignore all that. Why is that? Because there's a lot more interest and importance, I think, in the upstream determinants of health. And we're going to represent the causal web as multiple co-evolving dynamic relationships. So we're going to focus on one survey, the National Population Health Survey at Statistics Canada, started in 2004 up till 2010. And it's been linked to the death record, so we have mortality follow-up. We're going to estimate these multiple co-evolving relationships, incorporate it in the model, and we're going to use a visual or a graphic metric for health inequalities. And then we will display the impacts of 3 ameliorable causes. So that's sort of the bottom line of this analysis. And see, by estimating, working out the numbers, what the counterfactual impacts are. There were about 20,000 people in this survey. Most of the content is conventional health survey stuff, like sociodemographic stuff, chronic disease checklist, major risk factors. But there was also some more interesting and exploratory factors, something called Antonovsky's sense of coherence, sense of mastery. And most important for today's purposes, the Health Utility Index, which is a single scalar index of health status based on 8 dimensions, which I'll show in a second. Another really nifty thing about this survey, you have to praise the guys in the methodology branch of StatCan, is we all know that whenever you do a sample, there's sampling error. And the samples that Statistics Canada and other large national statistical offices do are rarely simple random samples. They're complicated sample designs, clustered multi-stage. So in order to enable users to estimate the variability, the variance in anything they produce, what the survey has is 500 different weight vectors. And what you can do, and each of the weight vectors, 60% of them are non-zero, so 60% of the records have a weight, and 40% don't. So the weight is identically 0. And what we did is we grabbed 40 of these weight vectors out of the 500, and instead of doing the usual goodness of fit kind of regressions, we used something fancier, which is we would estimate an equation on the 60% of the records that had non-zero weights, predict what the value would be for the 40% that had 0 weights, and iterate and adjust until we got the best fit of the data that way. And more specifically, fancy stuff, and so it's called the elastic net, which is a weighted average of ridge and lasso regression. Somebody said, oh, that's machine learning. And I said, well, I'm glad to learn that, but son of a gun, we did this a decade ago, and I'm glad the rest of the world is catching up, or whatever, giving it a nifty name. Now, the thing about this is we did this process 40 different times. And one of the things that happens is not only do you get a sense of the variability of the coefficients, you also get a sense of which coefficients are non-zero. And across the 40 bootstrap estimations, sometimes they're 0, sometimes they're not. So in a way, it includes specification error as well as sampling variability. And then what we did is we carried these 40 sets of regression. There were like 200 variables on the right-hand side here with 20 variables, so lots of coefficients, over to the simulation model. And we ran the simulation model 40 times, once with each set of 20 equations that had been bootstrapped. We're going to focus on the health utility index from the National Population Health Survey. So 1 is full health, 0 is good as dead. There are people whose health state is considered worse than dead, but we didn't observe any in the sample. And the 8 separately assessed attributes are vision, hearing, speech, mobility, dexterity, cognition, emotion, and pain. I put this on the survey because I thought it was really good to have, what health economists like to do is talk about qualities, quality adjusted life years. And we really needed a good generic quality for Canada and for health economics and cost effectiveness type stuff. But people started tabulating the results, and it turned out that pain was the #1 health problem. If you don't look at it, if you say, I'm not going to only consider cancer or heart disease, I'm going to look at these other factors, symptoms or whatever, aspects of health state. So that was fortuitous. So our plan is to focus on the determinants of health-adjusted life expectancy, which is a complicated object. So single equation approaches don't work, so simulation is essential. The specification of the functional forms were driven by our analytical objectives. An awful lot of epidemiology, you have a standard table 1, table 2, and you try and do your analysis so that you can fit all of your empirical results in whatever the 5 or 8 pages of a journal article. He set a pox on all that. We're going to feed this into a computer model. So if we have hundreds and thousands of coefficients, that's all right. We're not aiming to publish the coefficients. We're aiming to publish the more important results. And since A can affect changes in B with lags, and B can affect changes in A also with lags, we need equations that reflect co-evolving processes. So these are all the variables, the 20 or so variables that have been included. So you see the 8 variables that are part of the health utility index: income, leisure activity, smoking in 2 different ways, employment, family status, educational attainment, and so on. And the regression was basically 2-period lags. So we estimated the rightmost X and Y on the basis of going back 2 years. And this enabled us to have more than one observation on any one individual in the sample, which strengthens the ability to assess the fixed effects and other things. And then the counterfactual is we just override the transitions. I'll show some pictures of that in a minute. And we're going to assign a perfect score. Somebody said to me, Michael, what you're doing is sort of the knockout gene analogy in social epidemiology. So yeah, maybe that's what it is. So we estimate these results, and this picture implicitly says we have discrete time, and there are only a few of the arrows shown, but we allow arrows to go every which way. I just didn't want to have the image look totally black. And so the regression basically stepped along and said, we're going to get variables in the 3rd column as a function of the previous 2, then again and again, and then we're done estimating. And then we also want to be able to construct counterfactuals. So suppose we want to knock out the effect of socioeconomic status. So what we'll do is for each of the arrows that have the little ovals, circles there, we're going to say whatever the model is generating, we're going to override that and push, in this case, the counterfactual we assume is we're going to push everybody up into the 10th income decile and university graduate in terms of educational attainment. And we keep on doing that, here, 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 and so on. And then we do this not just hundreds or thousands, but we do it millions of times till we have a big sample. Because there's a lot of calls to the random number generator, there is Monte Carlo error, and we want to get that within bounds. And the Monte Carlo error is always going to be very small compared to the variety or the variation that you see related to the bootstrapping. Now, one issue that I've encountered with this thing is explainability of this thing, because it may look like, I hope I've given you at least an intuition of how the estimation and the modeling works, but what's going on inside it. So let me see if we can do this. So I'm going to show three visualizations here. What you can think of as the result of a simulation is we have 20 variables that are the state variables for each individual. We have years of age up to 100 or 110. And then we have jillions of people that have been, whose life histories, whose biographies have been synthesized. What we did here is we took out 500 people and randomly drew a subsample of 20. And what you see here with these little dots, which I'll just, if I can see where the heck they, so they're flickering on and off as people move between health states over the course of a simulation. Vertical dark lines are when people die, right? So everything goes dark. So that's one. Another one, if you take a different view and say, let me focus only on the health utility index, the summary health status number. This is how people's health status, and it's not monotone decreasing health status. People do recover, or they get treated if they get glasses or something like that. And then eventually people will go kind of dark. So that's another, the colors are really different here on my screen. So that's another sort of way of looking at the results of the model. Let me show one other thing here. And this is a radar plot showing, in this case, what are the main factors that are correlated with the health utility index, and how they evolve across the 500 individuals as we move across ages. I don't think I want to dwell on this too much, but the challenge here is trying to figure out ways when you have this highly multivariate, multidimensional thing that's being synthesized to enable people to have a look and see whether they're comfortable with what it's generating. We've found over the years that doing this kind of visualization really helps, not least in debugging the software, making sure it's generating things that are plausible. So here's a very simple first set of counterfactuals. So what we see here is health-adjusted life expectancy, and the change in health-adjusted life expectancy. If we say nobody has a problem with dexterity, or nobody has a problem with speech, or mobility, so those are the health utility index 8 domains. And what we see is there's quite a range of variability. And as I said, virtually all of this is from the bootstrapping. It's not from Monte Carlo error. And here's what it looks like for men and women and for life expectancy on the left, health-adjusted life expectancy. And let me just point out, pain in terms of life expectancy has 0. If we eliminate pain, it has 0 effect. But if we look at health-adjusted life expectancy, it looks to be the median of those 40 replicates is over 3 years. So it's far more important if we include measures of health status among the living in our health measures. This has been one of my objectives at Statistics Canada. I wish the rest of the world would do more. To say, come on, we got to get beyond just tabulating causes of death. That was far in the UK, 250 years ago. And similarly, pain here. So pain for women and cognition for men are the most discrepant between life expectancy and health-adjusted life expectancy. I've also done a couple further experiments where we have some composite. This is a bit tricky, so let me, we'd say, well, what if we got rid of obesity, BMI, body mass index? What if we got rid of smoking? What if we got rid of family membership? Being part of a family is protective. What if people all worked? And then SES as a composite variable, etc. So, and there's a number of caveats because these are associations. I don't want to claim causality here, even though they're lagged relationships. There are errors in variables. For example, we know that body mass index is underestimated in surveys where you don't, if the interview comes in with a scale and a tape measure, you get a better answer. But that is not usually the case. There are many omitted variables, so there's something called omitted variable bias, but I would contend that the number of omitted variables here is far less. And in effect, we've included what some folks call time-varying covariates explicitly. So both of those make big differences. If they're left out, you can get really misleading results in conventional epidemiological studies. This is estimated for a hypothetical 1976 birth cohort, and by that time, smoking had declined quite substantially in Canada, particularly for males. So this is what it looks like if BMI and other things were put at some nominal counterfactual level. So to start out with, mental conditions for life expectancy in HALE are hugely discrepant. So 6 years over there for health adjusted, this is men and women together, and 1 year on life expectancy. Here's sensory, which includes pain, but also vision, hearing, other things. Again, hugely discrepant. Body mass index, there's a lot of controversy about this, but there is good study that says that a BMI of 27 is actually better than having a BMI in the 20 to 25 range that WHO talks about. And in fact, our analysis supports the work from the CDC, National Center for Health Statistics, and says, well, actually, if we set the BMI to 27, everybody would be better off rather than their existing distribution. So we can have an extra dessert, right? Smoking, it's bad. If we got rid of it, it would raise health-adjusted life expectancy and life expectancy. Socioeconomic status is also important, at least as important as cancer. So there are some summary results from that. So let me now look at the three counterfactuals, which are kind of the punchline of the talk. We're going to be looking at LL. So life expectancy, LE. LL is life lengths. Since we've simulated jillions of individuals, we have a bag full of LLs, life lengths. And we also have a bag full of health-adjusted life lengths. And if you remember the little animation with the gray shade levels, basically what we're doing is we're taking the cumulative sum over that vector of health states for each simulated individual. And how are we going to make this work in terms of a univariate measure of health inequality? Well, here's that survival curve that we saw a la Julian Legrand. And I'm going to rotate it a little bit like this. And then what we can do is say, well, there's our line of health, zero univariate health inequality. And if we simulate a change where the line goes up and has a less steep slope so that the increase in life length or health-adjusted life length is bigger at the lower end, I should back up. We've sorted individuals by either their LL or their HALL and divided them in deciles. So if things go up more for the people who have the yuckiest health over their life course than they do for people who have good health, that's an equalizing change in univariate health inequality. And the opposite, if things go up more at the healthiest end of the horizontal axis, the health spectrum, that's a disequalizing change. So to summarize, I'm going to show graphs that have on the vertical axis the change in life length or the change in health-adjusted life length. So that would be an equalizing change and a disequalizing change. But before I show those, the first thing is to say, here is what the baseline simulation shows. So for example, the median male life expectancy comes out at about 88 years. The dashed lines are LLs, or life expectancy, solid lines, or health-adjusted life expectancy. The median female health-adjusted life expectancy is about 81, and the 90th percentile life length for all LLs, given all the heterogeneity, sampling, and specification errors, is quite high. And I was presenting this a little while ago, and Richard Pito was in the room, and he says, I don't believe any of the stuff you're showing me, Michael, because there's no way that people will have that kind of life length. But let me tell you my response, which is that this is not the median or the mean, this is the upper tail, and there's a lot of uncertainty from all of the bootstrapping and estimation. So we're not saying this is reality, this is plausible given the uncertainty in the data that we've used here in the analysis. So here's what happens when we get rid of smoking. So it's mildly equalizing for the change in life lengths for men. It's a bit more equalizing for the changes in health-adjusted life lengths for men. It goes up and down for women for life lengths, and similarly for health-adjusted life lengths. So to summarize the main points there, eliminating smoking increases life expectancy in HALE by medians of about 1 year for men, and about 2/10 of a year for women. For men, the smoking prevalence decreases with life length and health-adjusted life length, i.e. from left to right, excuse me, across the horizontal axis. So eliminating smoking for men is associated with a greater increase in lifetime health the poorer one's health is to start with. Right? So that's an equalizing change. For women, smoking is uncommon, at least based on our analysis, at the lowest levels of health-adjusted and life expectancy. Most common in the lower middle ranges, so that's why we get the humped pattern. Next, we're going to do SES. Anybody want to venture a guess about what happens when we put everybody as university graduate and in the 10th income decile? You're spellbound, I hope, or else really unsure where the hell this is going. Here we are. So it's mainly neutral for men. It's mostly disequalizing for women in terms of life lengths. It's mainly neutral for men in terms of health adjusted, and quite seriously disequalizing for women, particularly at the low end of the health spectrum. So again, in bullet point form, moving everyone always to the top of their SES category, by and large, is a really good thing because it's associated with about a 2-year increase in life length and HALE for men and 1 year for women. So on balance, it's really good. For men, it's relatively evenly spread throughout the lifetime distribution, so generally neutral for univariate health inequality. For women, improving socioeconomic status at the lowest levels has little impact. It is most important at the 3rd to 8th deciles of life length and health-adjusted life length. So having top SES for women is disequalizing, then flat, and then equalizing a bit as one moves up from left to right across the horizontal axis there. Last but not least, pain. Now, is anybody going to be a little more courageous and say what they expect the result to be? I think I have 7 more minutes, so I can wait a little while here. How many think it's going to be equalizing, eliminating pain? One brave person. How many think it's going to be disequalizing? Well, as John Burko would say, the nays have it. Here's what it looks like. And I have to say, I was really surprised when I got these results because I didn't believe them. And so we spent a lot of time digging into the model to make sure these results were right. So in terms of life lengths, and the numbers on the vertical axis are quite small, it's disequalizing for men, and for women, small, somewhat equalizing. But in terms of health-adjusted life expectancy, the numbers are much bigger, and it's strongly disequalizing. So what's going on? So for both men and women, eliminating pain has almost no impact on life lengths, about 0.2 of a year or less in most deciles. Pain has far larger impacts on health-adjusted life lengths. We already saw that. So greater than 4 years for women in most deciles, and about 1 to 2 years for men. For univariate health inequality for both men and women, the lower one's lifetime health, the smaller is the impact on health-adjusted life expectancy or life length of eliminating pain. So how can one possibly understand this? What's the intuition? And I can't prove this because we don't have all the variables in the model. But my conjecture is what's going on is the people who have the yuckiest life lengths, yucky being a very technical term for health status here, are suffering from things like mobility impairments or cognitive impairments, which are not associated with pain. Whereas the people in the upper half of the health status spectrum here have arthritis, right, which is very painful. And so the biggest benefits from eliminating pain are in the upper half of the distribution of health status across the population. So let me conclude, a bit early even. So the focus here has been on the full life cycle health-adjusted life expectancy as the key bottom line health indicator, which, as I hope I've persuaded you, is far more important than conventional and ubiquitous life expectancy. I wouldn't say it's easy to collect cause of death or mortality rates, especially in third world countries, but it is by far the most common health indicator for the population. It's a lousy indicator. It's very misleading. We spend a lot of money on cancer and heart disease and not nearly as much on pain. A bit more on dementia maybe, the cognitive impairments. Understanding the impacts of health determinants requires more than piecemeal epidemiology. There are journals and journals filled with, I'm going to regress this on one factor, or maybe 2 or 3. What this is showing, I guess I could show it more vividly if I did more snipping of the causal pathways, is you're missing an awful lot if you just do that kind of little bit at a time epidemiology. It also is a message for national statistical offices and things like EU Silk to say you guys really ought to do a better job in the way you run your health surveys, and share for that matter. In assessing the justness of health inequalities, and this is not at all what I entered this project feeling, we really have to go back to a Julian Legrand style of univariate, not bivariate measure of health, more Chris Murray than Michael Marmot. And there are some surprising and in some cases here really counterintuitive results. Yes, eliminating smoking would be generally equalizing. Improving SES seems to be generally neutral and a bit weird for women in poor health. And most strikingly, eliminating pain is disequalizing. So thank you very much.